Hi everybody. This is Obi-Wan Pez. I am starting to echo. I don't understand. Check.
It's interesting. It's probably off the webcam. Check. Okay, this is really weird. Webcam off. Beauty. Desktop. That's so weird. If anyone is here, apologies. Check.
Check. Hey, there we go. Alright, so apparently the problem I was at... No, I'm still getting some echo. Where's this? Check. I'm still getting a little tiny bit of echo in this, and it's driving me insane. Anyway, if anyone is here, welcome. This is Obi-Wan Pez for Ensign Flex Pachinko. I attempted to do a math stream yesterday, but apparently Twitch was having some connectivity issues, and I couldn't actually get connected at all. Alright, check again. Check. Just slightly there. Check, check, check. Check, 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 check. Alright, so do something like this. See if this helps any. Not really. Curses. Check. Yep, still there. One of the whole reasons that I switched over to OBS for tonight was that the Streamlabs stuff was not working properly and was coming up with this echo, which had never happened before. Still sounds pretty bad. Alright. Well, guess we're just going to have to deal with it for tonight, and in the meantime try to figure out what is going on. Because literally I changed none of my audio settings in this entire thing. But hey, this is what I get, right? Alright. If we apply, that didn't change anything. Okay. Check. Hello? Check. Check. Still happening. Alright, well, just gonna have to deal with it for tonight. And like I said, figure out what's wrong later. I don't like it. Alright, so for tonight, I figured we'd do a little bit of calculus to start, and then see what else anybody else is coming around with. If anything, that's fine. I suppose the problem is just that both programs are open. Nope, not so much. Oh, oh, hey, that did it. Awesome. Okay, so pro tip, don't have both Streamlabs and OBS open at the same time. So apparently one was feeding through the other and causing it to feedback. Oh man, it has been a day. Alright, so here's how we're doing things. Just double check real quick. Yeah. Yep, good times. Alright, so where I was going to go with this tonight is that we were going to talk about first a little bit of calculus, and specifically what happens when you're talking about two kind of random functions that are just out in space doing whatever they're doing. And if you want to find the area of the curve that is between these particular functions from any particular place, and it doesn't have to be here, from any particular place A to any other particular place B. So here we have f of x is going to be our upper function for the sake of argument. G of x is going to be the lower function for the sake of argument. It does not matter which one you pick. So there are a few ways to go and think about this. One is that, right, you only want the area that's in between these two curves here. We do not want the area that is beneath G. So this is like some of the other, geometric problems you've seen before. What is the area of this? Here, let's stay consistent. What is the area of this figure here? Which is basically just a rectangle with a hole in it. So in much the same way that you would think about this as, okay, well, let's look at the whole picture first, and then let's break down little pieces of it. In this case, we would take, again, the area of the rectangle and then subtract the area of the circle. It's totally a circle. And that ends up getting you the area of this thing. So that is one option. And in looking at this particular setup, we basically are doing the same thing. You want to look at this in terms of the calculus itself. What have we seen before? Well, the area under a particular curve, let's say f, is going to be the entire area, which is red and blue together. And the area under a curve is represented by the definite integral from a to b on f of x dx. And then here, we know that the integral from a to b for g of x dx, that's unnecessary, g of x dx is going to be equal to that blue section. All right, f of x dx, when you take its integral, is going to be equal to the red section with the blue section. So if we want to get the area of the red section only, then what do we need to do? Well, we take the section that is both the red and the blue, and then we subtract out the blue part. So we get only the red part. So how do we do that? Well, I've got it right here, right? This is going to be the area the integral from a to b on f of x dx minus integral from a to b of g of x dx. Now, there's also another way to think about this. Mathematically speaking, if you... Cloudfloofs, good evening. Which part do you mean by reducing? So if you give me an example problem, I will be happy to help you out with the idea for it. It's my only complaint is that there are many different ways that you could use the words reducing. So that's my hang-up. Simplification of fractions, I think, really is... Okay, so do that one in just a second. And realistically, what you've got here, you could probably do this in terms of this kind of calculus because, quite frankly, this is just a bunch of geometry. The notation might be a little bit tricky, but, you know. Alright, so here we can combine these two integrals into one, make it the integral from a to b of f of x minus g of x dx. And so that's going to work. Also, you could think of it another way. If you go way back over to here, we could look at this and say, all right, if you're looking at any particular point along the entire stretch from a to b, then what we're looking for the integral is going to be this little tiny dx wide bar here, and your y value at the top is going to be f at that particular x, and your value at the bottom is going to be g at that particular x. So how do you find the distance between two objects? I do this almost every week. How do you do this? How do you find the distance between two objects? You subtract them. So f of x, any particular point along this entire stretch, minus g of x, the lower part, anywhere along this particular function. And then we're multiplying by dx because that's our width. So geometrically speaking, this is just length times width. Again, the notation's a little tricky, but it works. Okay, so in terms of reducing fractions, the first thing that you want to be able to do. So let's go with 438. Yeah, 438 divided by 210. Now, I don't actually have any particular knowledge about these numbers, so we're just going to try to figure out what here can be divided out from both of these pieces. There are a few simple ways that you can check like what kinds of numbers are divisible or which exact numbers are divisible from other numbers. So one way to do that is to look at the... Yeah, that's okay. Maybe we'll do a simpler example, but we'll work our way up to this one. Alright, so basic idea, no matter how complicated this is that we still want to check and make sure that alright. Okay. It's yelling at me for some reason. So the basic idea here is that we want to find any particular numbers which are represented both on the top and on the bottom, so that what we can get is something that looks like some number divided by some other number, doesn't matter what it is, times something that looks like 2 over 2. Oops, that's not a 2. 2 over 2. And or something that looks like 7 over 7. Anything like this. Because these particular numbers, if you multiply by a 7 up top and also a 7 on the bottom, then this is a form of 1, right? This is the number 1. It's just in disguise. So 7 divided by 7, you can divide out both top and bottom. 7 divided by 7 gets you a 1 on the top, a 1 on the bottom. Or just a 1 overall as a whole number here. So this would be a 1. And then a 2 divided by 2 is also going to be 1 over 1 or just 1. And eventually what we want is that our original fraction over here is going to eventually be looking like something that is a number divided by another number. And, right, as you said, they will be reduced values. They will, however, have the same ratio to each other. So if you divide 438 divided by 210 in your calculator, and you divide our new number, a divided by b, whatever it turns out to be, at the end, you will always get the exact same values. If you don't, you did something wrong. You need to go through and check again. All right, so in order to be divisible by some number, our number over here, you know what, let's make it easier. So let's do 48 divided by 63. Oh yeah, I know, but and typically I don't either. We only allow our 4-function calculators. I work at a two-year college institution, and we only allow 4-function calculators at this level. Once they start getting into stuff where they actually have to graph, we do, like, when I say have to graph, I mean when the graphing itself is no longer part of the lesson. So it would probably be the equivalent of Algebra 2 in high school. So once students get to the Algebra 2 level, generally we allow them to have graphing calculators, but only for verification, because they still have to do out all of the work to make sure that everything is there. So if we take numbers like this, 48, 63, what we want to do is look at what numbers are going to be divisible. What numbers can be divided evenly into, painted myself into a corner there, what numbers can be divided evenly into both 48 and 63? So one way to do this is to just break down each of these numbers into their smallest bits. These are what are called prime factors. So prime factors are going to be evenly divisible only by 1 and themselves. So the prime numbers start with the number 2, 3, 4 is divisible by 2, so that doesn't work. 5, 6 is also divisible by 2, 7 is not divisible by any of these numbers so far, 8 is divisible by 2, 9 is divisible by 3, 10 is divisible by 5, 11 is not, 12 is divisible by 2, 13, 14 by 2, 15 by 3 and 5, 16 by 2, 17, 18 by 2, 19, and 20 also by 2. Anyway, this will keep going, but honestly, these are the numbers you're mostly going to be using, numbers less than 20. So when we look at this, you can tell fairly easily which of these numbers you're going to be able to divide into 48 and 63, fairly simply. There are certain like memorizations that people do, and yeah, it works, I guess. But for now, if you were to, there's a whole number of different ways that you can work out the kinds of patterns, but what I'm going to say for this is that if you want to know if something is divisible by 2, right, it will end in an even number. So 0, 2, 4, 6, and 8 are going to be the last one digit. All of the numbers that are divisible by 3 have this really weird thing about them. Is going to be that the sum of all the digits that are in that number are divisible by 3. Is. The sum is. And it is repeatable. So if we wanted to know whether, let's go over here, 438 was divisible by 3, we could say, for example, that 4 plus 3 plus 8 is equal to 4 and 8 is 12 plus 3 is 15. And if we didn't know that this was already divisible by 3, you could also add these numbers. So 1 plus 5 is equal to 6. 6 is divisible by 3, therefore 438 is also divisible by 3. And we could also do the same thing for 48. Looking at this, you can see that 48 is divisible by 3 because you add up the two numbers. 4 and 8 make 12. 12 is divisible by 3, or 1 plus 2 is 3, which is also divisible by 3. It's also divisible by 2 because it ends in a 2. So we can divide 48 nicely by both 2 and 3. We'll come back to more in just a bit. 4, if you want to know whether a number is divisible by 4, it will end in a 2-digit multiple of 4. So this is stuff like, 04, 08, 12, 16, 24, and we can go on from there all the way up through 88, 92, 96, and double zeros. So all of these combinations are going to be divisible by 4, and any number that has these as their last two digits will also be divisible by 4. The number 5 will end in either a 0 or a 5, which is itself a multiple of 5, essentially what we're saying. 6 is if a number is divisible by 6, it is divisible by both 2 and 3 at the same time. So here you look at these two. It has to end in an even number, and you have to add up all of the digits to be a multiple of 3. 7 is evil, and so I skip it typically. So if a number is divisible by 8, this will end in a 3-digit multiple of 8. So you're going to end up with something like 128, or, curse myself. Yeah, 512, 520. Let's do one that's not a nice multiple of 2. 528, 8 times 656. Just as some examples. So we can throw out these numbers. If the whole number itself is divisible by 8, you'd only have to look at the last 3. And last one here, if it's divisible by 9, right, the sum of all the digits is divisible by 9. Or you will eventually, if you just keep repeating this over and over and over again, it will become 9 itself. Now, I at first thought this was completely absurd. Like, why would that happen? No, no, no. Okay, so I've got a number here, which is 244,944. This is a really big number. I would not want to figure out by hand if this one isn't too bad, but I don't necessarily have to go through the division algorithm to divide by 9, do that whole big division thing, and then get an answer as to whether this is divided by 9, whether 9 divides it evenly. Instead, what I can do is just real quick go right through all these numbers. 2 plus 4 plus 4 plus 9 plus 4 plus 4. Add these up. This is going to be 9 and an 8 is 17, 4 is 21, and another 6 is 27. That adds up to 27. 2 plus 7 adds up to 9. So 244,944 adds up to 9. Or, sorry, is divisible by 9. It does not add to 9. There we go. 244,944 is divisible by 9. And if we actually do it out, it's 9 times 27,216, which again, you can figure some of this stuff out pretty easily. So if you're just looking for individual prime factors, this is a good way to do it. You don't necessarily have to memorize this whole list, but just get used to it. Kind of refer back to the list and check it out and see if it makes sense for you. All right. Yeah, okay. So 7 is the odd one out. So So I'm going to do one that is divisible by 7. I'm just going to take 7 and multiply it by some absurdly large number. Actually, that's a bad idea. 7 times. A 4-digit number is going to get me a 5-digit number. And so I'm going to do, this is 39,501. Alright, so what we're going to do here is we're going to take this last number and double it. This is going to become 3,950 minus the doubled number here is 1 doubled is 2. This is now 3,948. Now we take the last number here, the 8, and we subtract 394 minus doubled 8 is 16. And as absurd as this is, it always works. Okay, so then 394 minus 16 is going to be 378. 378. And again, we have an 8 as the last digit. Now we can take 37 and subtract 16 from it, which is, again, 8 doubled. 37 minus 16 is going to be a 21. 21 is divisible by 7, therefore 39,501 is also divisible by 7. I don't like using this divisibility rule because it gets confusing. Nobody likes it. It is very powerful and nice to use and all that, but... So the ones that you're typically going to find, at least at first, stuff like 48 over 63, you're going to look at this and say, okay, let's try and figure out what all of these will break into. So what kinds of numbers divide into 48? Well, if you look at it, it ends, first of all, it's only 2 digits long. So we have the option of looking at potentially 4 or maybe 8. And if you remember your multiplication tables, this should start coming back. If you don't remember your multiplication tables, or if this is a much bigger number, you might want to fall back on some of these other rules, which we already said. Again, it's divisible by 2 because it ends in an even number. And it's divisible by 3 because we can add up the two numbers and get a multiple of 3. Again, namely 12. Now when we do that, notice that this is now divisible by both 2 and 3, therefore it must be divisible by 6. And again, if you remember your multiplication tables, this is not a particularly difficult one to remember. It is 6 by 8. So 6 by 8. Also, we could look at this and say, well, both of these numbers individually are multiples of 4. So if we were doing the division algorithm, you divide your tens place by 4, and you get a 1, and you have none left over, and then you divide your ones place by 4, and you get a 2. So 4 and 12 would be decent factors for this. So it's kind of your pick as far as what you want to divide it into. And there's a few different ways that you can like bookkeep this stuff to make sure that you are only hitting numbers that you want, or you're not accidentally leaving some off your list, because that gets embarrassing sometimes. I still do it, don't worry. But anyway, if we're looking at 48, and if we want to look at prime factors, one of the things that you can do here is you could say, all right, 48 will break into, we already said 4 and 12. 4 times 12, or 2 times 24, or 6 times 8. Take your pick, right? Doesn't actually matter which one you want to do. If you want to look at, you know, what are also the factors of 63, then it might be handy to do one of these other than or instead of the other. But as it stands right now, 48 can break into any of these things. If you want to break these up individually further into prime factors, then you're going to look at what makes up each of these types of numbers. So here, 6 and 8, the 6 will break up into a 2 and a 3, and 8 breaks up into 2 and 4, and 4 breaks up into 2 and 2. So the prime factorization for 48 is this line here, which is 2 times 2 times 2 times 2 times 3. If you only wanted to multiply or get it into a multiplier version, then these are perfectly fine. You don't have to go any further. As long as you have something in common with the 63, then you're good. This also tells you the prime factorization allows you to see what other numbers you could make out of this. Because you don't have to only get, right? Like here, I didn't actually have a 3. I didn't put 3 down as one of the numbers that we can multiply by. But we could have. So if you do this, you would look at the prime factorization and say, well, if 3 is going to be my first number, then the 4 2's that are here are going to be my second number. So what pair does that make? It's 3 times 2 times 2 is 4, times 2 is 8, times 2 again is 16. So 3 times 16 is another option that I skipped up here. Then if we look at 63, again, if you remember back to your multiplication tables, then you already know what it is. You're good. If you don't remember your multiplication tables, or you need to work out what this is, it's a larger number than actually 63, like our 438 and 210 from earlier, then it would be easier to say, okay, what divisibility rules do we even see here? First of all, both of these numbers multiply up, or no, both of these numbers add up. 6 plus 3 is 9. Therefore, 63 is divisible by 9. And or, if this is getting troublesome, like you don't remember how to divide 9 into 63, you don't remember your multiplication tables that high, you could also say, okay, well, 9 is made up of 3 and 3. So we know that 63 is equal to 9 times something. And if we don't know what that is, that's okay. We can break this up into 3 times 3 times something, whatever that might be. And then you say, okay, let's try to work out what this other stuff is. So if 3 is one of your divisibility factors here, then we could divide 63 by 3. So if we divide 60 by 3, we end up getting a 20. And then we have none left over. Now this is 3 into 3 goes once. So 63 is equal to 3 by 21. 21, that's a much easier one. If, again, this is a low number on your multiplication tables, so it's easy enough to figure this one out. This is 3 and 7. So 63 is going to be 3 times 3 times 7. Now, when you look at both of these things, this is when you can say, now what's common to both of these pieces? We have a 3 up top and a 3 down bottom. we could divide both top and bottom by 3, and that'd be it. So, those are the only common pieces. So this is a 2 times a 2 times a 2 times a 2 over a 3 times a 7 times a 3 divided by 3. Alright, all we've done here is just rearrange how the multiplication works, and then associated the 3 with the 3 in order to divide them out. So, these end up just getting us a 1. 2 times 2 times 2 times 2, we already did this, that was 16. Divided by 7 times 3, we already did that, that's 21. So, 48 over 63 is going to be equivalent to 16 over 21. In order to figure out, like, intuitively, how big is that? Is it, like, close to a certain number or something like that? This gets a little bit hard sometimes to visualize what this fraction really means. It's not 3/4. It's not 5/8. Something simple. 16/21 is rather complicated when you just look at, like, how big are these things. You could estimate it. You could plug it into your calculator, you know, by yourself and figure out decimal. Where is this approximately? But in terms of just like doing kind of a common sense, is this correct or does it seem reasonable? You know, you can look at the individual values here and say that we're missing, you know, 16 out of 21 is missing 5/21 from being a whole number, and 5 out of 21 is really close to 5 over 20. 5 over 20 is 1/4, so we're pretty close to 3/4 here. 16/21 is really close to 3/4. So then what about 48 over 63? Does that work out about the same too? Well, 64 would be a nice multiple of 4. And that's really close to 63. And 48 out of 64, again, is going to be missing a 16. So then 16 out of 64, yeah, that's actually 1/4 as well. So just from looking at it and kind of estimating approximately how much is this, we're seeing that, yeah, we are really close to 3/4 for both of these numbers. Again, that's just a sanity check. I don't recommend writing that out anywhere. For the number 438 over 210, you're really not going to change the process any. It's a bigger number, but it doesn't matter. You're going to do the same thing. So here we can look at this and say, okay, 4 and 3 and 8 are going to add up again to 12 plus 3 is 15. 15 is divisible by 3, or then it comes out to be 6, which is divisible by 3. Either way. So 438 is going to be immediately divisible by 6. You can just tell instantaneously that's going to happen. Also, that's behind my head. You can't see that. Also, 210. 2 plus 1 is 3, plus 0 is also 3. That's divisible by 3. And it ends in a 0, so it's an even number. So, this is also divisible by 6. Is that the greatest common factor? No, probably not. But we have found at least a common factor that we can divide out from both of these pieces to make the problem easier overall. So 438, I would recommend doing division algorithm off of this, saying, okay, 438 divided by 6. If you need to, you could divide it by 2 and divide it by 3 in quick succession. I'm okay with 6s, so that's, you know, personal preference. So 6 into 43 is going to go 7 times to get us 42. Subtract that, we're left with a 1. That leaves us with an 18, and 6 into 18 is going to go 3 times, which is 18, which leaves us with 0. Yes, technically you want to bring this down, make it 18 down there. I'm also fairly bad because sometimes I do shortcuts. All right, so here we get a 0 remainder, 6 times 73. All right, then 210. 210 divided by 6. Okay, well, we can do that. That's fine. Right, 6 into 21 goes 3 times to get us 18. Then that leaves us with 3. Drop the 0, becomes 30. 6 into 30 goes 5 times exactly. So now 210 is 6 by 35. So, our fraction 438 divided by 210 is equivalent to the fraction 6 by 73 divided by 6 by 35. And again, here we can associate these two together and say, well, look, this is a 6 divided by 6. So we'll get rid of those. Divide 1 divided by 1. So now we have 73 35ths is going to be the fraction that's left over. No worries. Where we leave off. No, don't worry, man. Yeah, quite honestly, I will still literally teach anything to a blank room. It's perfectly fine. I have 0 expectations for Twitch. And always, I'm not going to like get mad or something like that, because, even if you did go away for no reason at all, like that's fine. Yeah, I'm not gonna get angry about this. This is just for fun, really. And you can always check video on demand. So I mean, I'm not gonna like badmouth anybody for leaving because they can see it. That's a terrible idea. But anyway, yeah. So 438 over 210. Right, we got 6 by 73 over 6 by 35. We can divide out the 6's, 73 over 35. Okay, so with 73 35ths, now we have to just check a couple of things. So, the easier number to check here is 35. I know instantaneously, right, 35 is a nice number off of the multiplication table. This is 5 times 7. Done. Right? So 35 is 5 times 7. 73, we need to just check. We don't have to check all those divisibilities that are up top, unless you feel like it. It's a good exercise, but what you have to check it against is it divisible by 5? And the answer there is, well, no, obviously not, because, like we saw earlier, divisibility in 5 means it ends in a 0 or a 5. 73 does not. Okay, and then 7 is the evil one. However, all I said... well, actually, you know what? It's easy in this case. If we double the last number and then subtract it from the rest, we should get something that's divisible by 7. double the last number is 6. Subtract it from what's left is 7. 7 minus 6 is 1. 1 is not divisible by 7. So that doesn't work. 73 is neither divisible by 5 nor divisible by 7. These are what are called mutually prime numbers. So they don't share any common factors. They themselves are not prime numbers, necessarily. All it means is that they don't have any common factors with each other. So 73 and 35 are mutually prime. No common factors. Ugh. My handwriting is sliding. It's because I haven't been doing this on a daily basis. So, since they have no common factors, this is the simplest version of this fraction that we could get. 73 over 35 is equivalent to 438 over 210, and it is the simplest version of that fraction. Yeah. So, no problem, Cloudflus. If you need to leave at any point, feel free, and, you know, my on-demand video is always available to you. If you end up disappearing, or if you've already disappeared, that's perfectly fine. Don't worry about it. But if you have any other questions or anything like that, feel free to drop in. I do math streams usually on Wednesday nights. That's why the title down there says I'm a day late. And there's a good possibility that over the coming weeks, I'm going to probably do like a short daily math stream. And then like Wednesday night is going to be my big one. And then Friday nights I do some gaming, and other nights I will do gaming if I feel like it. So feel free to stop in anytime you want. It is technically a mature channel. All that really means is that I don't watch my mouth. So, you know, take that with a grain of salt. Oh, and the games I play definitely could be rated M for mature all over the place. But yeah, hey, if you wanna ask any more questions, feel free. And this goes to anybody else out there as well. My touche. So, I also have an email address if anyone wants to send individual problems or stuff like that. That's just going to be nsimplexpachinko@gmail.com. And yeah, I will, do research over the week if it requires research, and if not, I will throw it either into one of the daily math streams, daily-ish. One of my short ones that I eventually get to at some point, or the longer one on Wednesday night. And I'll try and, I guess, let you know somehow. Probably send an email back or whatever. Let you know when that's going to get gotten to. One thing to note, and this is not targeting you or anything. One thing to note is that I will not do like literal homework problems. Right? My big thing, I'm a teacher. I've been a teacher for 15 years almost. My big thing is that you really got to know how to do it yourself, and if you don't, then you're just cheating yourself out of a greater understanding of how the world works and whatever else, If I'm going to try to help you to learn the mathematics as best as possible through many different examples, and eventually to try to generalize stuff so that you would be able to come across any problem and just be like, oh, yeah, I know how to do that. That guy on Twitch told me. So yeah, coming up with like factor pairs or least common multiple or greatest common factor or anything like that, those get rather interesting. So, as far as like notation goes, and don't use this, but what we were really doing here, what we were really doing with 438 and 210 was we were looking for the greatest common factor. So the GCF of 210, 438, we went through all this process by hand. And we found out that the greatest common factor between these two numbers was 6. There are computer programs which can do this stuff for you. It's not a hard problem to solve, but at the same time, obviously, again, you don't want to use this until you're really familiar with, like, the math behind it and how the actual programming works. One of the things that happened to me in my middle school days was that our algebra teacher said, okay, you all have a bunch of graphing calculators, and this was Algebra 1 in 8th grade. So technically a little bit ahead, but whatever. Compared to today, like, it's amazing. I got students who come in like 4 grades above level. It's insane. I was only 1. So anyway, when you're doing stuff like greatest common factor, he was like, okay, look, I know that every single one of you has downloaded, like, programs from TI that have gone onto your TI calculators that will do all sorts of stuff for you that, like, are all automatic, everything. You can keep those on there, but only if you have programmed it yourself. And I was like, oh, that's a good trick. So we ended up spending a bunch of lunch breaks together, and we ended up creating the quadratic formula as a program, figuring out greatest common factors between two numbers. Like, there was a whole list of programs that we created ourselves, and understanding the input-output language and all that. It was pretty good. And it got all of us into programming at a very low level. So it really helped form some later structure. All right, what else we got? So Cloud Floofs, I'm actually specialized in pre-calculus. Really, is where I have most of my experience. I have done a lot of work with calculus and a lot of work with differential equations, which is like sophomore level of college, basically. Anybody who's going into one of the STEM fields, science, tech, engineering, math, is generally going to be taking differential equations and or linear algebra and or calculus 3. Those are like the 3 that are up there. I don't know, that doesn't necessarily mean much, but it's been a fun experience learning about all of the math and everything. So I actually have a bachelor's in mathematics education at the secondary level. So I was going to get my teaching license in 7 through 12 was going to be my specialization. And again, this was about 15 years ago. I ended up going into high school math and teaching at the geometry algebra 1, algebra 2 level for 2 years. And then I got frustrated with public schools. Among other things, I almost got punched out on the last day of classes because some kid didn't know that I was a teacher because I was like 24 and clean shaven, and I looked pretty young. And we were all dressed in it was the last day of school, so we were all dressed in like polo shirts and jeans. So I very brilliantly tried to break up a fight, and the kid was like, "Man, uh, that was a day." Um, so, yeah. So, I don't recommend that. Although these days, if I were to attempt to break up a fight, one, I have a brown belt in Tang Soo Do Karate, and two, I am much larger than I was. So it was an interesting experience. But after that, I was like, yeah, I can't. I'm not coming back to that school. That's clear. B, I was like, all right, I'm going to apply to the public schools in my actual location, like in my actual area around my house. Um, and it turned out that like when I started the application process, they were like, "Oh, and your references are now out of date." And I'm like, "All right, nobody knows me. Like I've got 5 people who might be able to send me a reference, and quite frankly, uh, 3 of them take forever to do it." So I was just like, I'm giving up. So I didn't go back to public school. Instead, I went to our local community college and said, "Do you need an adjunct?" And they were like, "Yeah, we're always hiring adjuncts. Come on in." So this was the place where I was taking classes to finish my teaching certificate. And I was let go from that job earlier because they didn't like the way that I was teaching, and it wasn't like yeah. Yeah. How dare you? Ugh, kids. Yeah, I gotta. I mean, what you see is what you get. I was always kind of a nerd. So, like, slightly athletic, but always a nerd. And, like, I didn't like the school teams and stuff like that. I was on the cross country team, which is a very individual sport. You don't have to, like, interact with people. Um, you're not competing with anyone necessarily at your school and all that. And, like, the competitors that I was competing against, like from other school, I didn't know who they were. They weren't gonna like attack me or anything in the woods or whatever. So it was like, whatever, it's fine. It's an individual sport. I'm just racing against myself. um, yeah, the most like hectic going to get beat up moment was like in 8th grade, I think. Some kid decided he was gonna trip me during our warm-up laps in gym because I was trying. Because again, running was my sport. So like I would go like do basic I would basically run a 200 while everybody else is doing their silly little jogs like this going like 1/2 mile an hour, and I'm just like, nope. So the kid tried to trip me and I was just like it was stupid. I shouldn't have done it. I like tried to jump back at him and he just kind of like tossed me aside. So it was stupid. I shouldn't have done it, but you know, it just I had had enough. I snapped, and it takes a lot, but especially in those days, I was very zen. Anyway, yeah. So I was working at this community college where I'd taken a couple of classes, and they were like, "Oh yeah." Yeah, we had like 4 major competitors on our cross country and track teams who in any given sport, like 1 or 2 in any given sport and 4 to 6 in total who were like super competitive, and I looked up to them and I hung around them because I didn't want to like, you know, I don't want to get distracted by all the other people who are complaining. And I will say, not much has changed in 20 some odd years. Yeah, so I started working at this community college, and they were like, "Oh, well, come on over. Let's, you know, do a sample lesson for us." And so I just like threw out the exact same thing that I did this other place in the public school where I was dismissed because they didn't like it. And so I got up in front and I did this thing, and the people were all just like, "Oh, this is wonderful. You know how to teach." I'm like, yeah. Thought that was a prerequisite. So, fast forward 3.5 years later, permanent position opens up, and they were like, "You should apply." So I ended up getting that position, and I haven't looked back since. I haven't really wanted to get back into public school. That being said, I could probably go back to public school now and be so much better of a teacher than I ever was, you know, fresh out of college. Um, I mean, obviously, I have experience now, but like I get a lot more of the like differing modes of thinking. I could never put up with the parents again, or putting up with the students just being like, I'm not going to do it, and being like, let's motivate you. Like, that's not going to happen. I'm in college now, and looking at the college students, I'm basically saying, like, I will keep sending you emails to tell you that you need to do your stuff, but quite frankly, if you don't show up after day one, like, that's on you. And the coffee's better. And this whole year has been really messed up for everybody. But yeah, I've been spending the last 3 months basically doing Twitch streams, and yeah, people actually like this. You know, I mean, it's I am no substitute for anybody else's like in-person teacher, but I can go off and, you know, have discussions with students about like this, about anything, and you know, whether math related or not, and I don't have to feel guilty about you know, wasting time. And it's not really wasting time, right? If you're learning something about life. As long as you're happy, you know, as long as you're having fun, as long as I'm having fun, we're all good. Yeah, when I got into college, a lot of the like math that we had started talking about really got into, or really got pulled into programming. And so when I started actually doing programming, I was like, this is amazing. Like, you know, we're talking about all these little things that are now getting all tied together. And, you know, the greatest common factor, there's, you know, I don't even know. There's just hundreds of little tiny things within mathematics that you would never even think of. And then, you know, you get to that point in school where everybody's like, well, when am I ever going to use this? And all of those little things where I was like, I never really thought about it too hard in terms of like, when am I ever going to use this? Because quite frankly, I was more into the idea of, I'm going to just learn everything I can about it because it's just cool. And then someday maybe it'll be useful. I mean, at that point, I probably should have realized that I was going to go into math. I was originally into physics, and that didn't go so well after I realized the second semester. Yeah. Woo. Yeah. Yep. That's always fun. You mean like tomorrow, Friday, right? So let me know if there's anything else you want to talk about. Because I will help you try to understand this as deeply as possible. Oh, starting to wish I have that fan. My mates. Where in the world are you from? Approximately. Doesn't have to be. Alright, so like, what about integers? Ah, okay. Yeah, I'm on East Coast of America, so just didn't want to, like, wanted to make sure you weren't, England or something where 4 hours ahead, already 2 in the morning or whatever. That would have been awful. Anyway. Yeah, I started using a lot of BBC type lingo because, well, that's my main source of media, is listening to the BBC. Yeah. Reading a ton of Douglas Adams. All right, so what specifically about integers? That's kind of a broad topic, but so if you're talking like, addition, subtraction, multiplication, division, using fractions, well, I guess using fractions technically is not part of integers, but anyway. So the idea of just integers in general stems from what's called set theory. And I've already done videos on this, but I'll give you a basic overview. And again, 7th grade, so I need to relax a little bit. So set theory is from this guy Georg Cantor, who was a German mathematician in the 1850s, basically. So the idea that he had was he wanted to classify numbers into different groups. And he thought, okay, let's break numbers down to their smallest group that we possibly can. So in the smallest group, he put what are called natural numbers. Or counting numbers. So when you think about counting, you think, okay, start. Well, that would be 1, 2, 3, 4, etc. Okay. So natural numbers, he also gave a symbol to each of these sets. So natural numbers was a double n. So the first bar is doubled, and then it's an n once you write it. So natural numbers end up being these numbers, starting with 1 and then moving up. The wonderful thing about the whole idea behind set theory is when you break math down to its very fundamental parts. And this also comes up in a class which is called abstract algebra. This is a junior level college level math majors class. So if you are majoring in mathematics and you are up to your junior level, so 3 years of studying, you start talking about abstract algebra and breaking numbers down into these groups and then talking about like what kind of properties do these numbers have. And it is literally abstract. So you're doing this in terms of like, let's just pick any number from this counting number set and just call it A. And it gets really technical really quickly. So again, we're not going there. But just looking at this, if you were to do something like add any two numbers that you could find in the natural numbers, right? Just add them. You're always going to end up with another number in the natural numbers. So if we pick just two values, you know, natural 1 plus natural 2, we're going to get some third natural number. This is what is called closed under addition. So, add up two natural numbers, you always get a natural number back. Same with multiplication. So, n1 times n2 is going to be some other n3. It's also going to be closed under multiplication. So this is like a really interesting property. You probably don't need to know that, but it is kind of helpful to remember back in the, back of your head somewhere that this is what's going to happen. If you end up with two numbers, you try to multiply them together, like what kinds of numbers can you get back? So again, natural numbers, add or multiply, you always end up with another natural number. The problem comes when you say, what happens if we try to subtract? Or to, more technically, find the inverse number. So for addition, when you try to find the additive inverse of a particular number, what you're trying to do is find the number which, when you add it to the original number, you're going to end up with what's called the identity. For addition, the identity is the number when you add it, it comes back to the same number you started with over and over and over again. So additive identity is going to be 0.
And now it's available for everyone.
So a plus some number equals a. Well, we already know this, right? Okay, clearly this is going to be 0. So the additive identity is the number 0. So here, the other thing ends up being the additive inverse is a plus some number, which gets us 0 back. For additive inverse, we know that this is going to be the opposite of a, or negative a. Again, no matter what number you started with, the negative of that number when you add it is going to get you back to 0. Now here's the thing. Those don't exist here, right? Just within the natural numbers, you don't have any negative numbers of any number. And in fact, you don't even have 0. There's no identity here. So Cantor said, okay, the natural numbers are this small group that we can talk about, but we can't just stop there. We have to expand it further because we need these properties. We need the identity and the inverse in order to have addition be a useful thing. So he expanded it and said, if you include 0, the identity, and all of those numbers on the opposite side, so all of those negative numbers, then we're going to have stuff like -3, -2, -1, 0, 1, 2, 3, etc. in both directions. These are what are called the integers. And they occupy a space that includes the natural numbers. So again, looking at it, the natural numbers are here. They are also in the integer group here, starting with 1 and just counting up. Integers in German is Zahlen, and so it has a doubled Z letter as its symbol. Again, you don't need to know that, but this will crop up every so often, and you'll be like, why Z? I don't get it. This is why. Right? It's a German word meaning integers, Zahlen. Now for integers, now we have the additive bonus, or additional bonus. We have the additive identity, 0. We have all of our additive inverses, -1, -2, -3, etc. And if we pick a number, -3, and try to find its additive inverse, what number, when you add it, gets you 0? It's the negative of -3, which is +3. All right, then we look at multiplication. So the multiplicative identity is going to be the number which, when you take some number a and you multiply by whatever this is, you are going to end up with a back again. Okay, well that one's easy. We know what this is. This is, again, just a number. It's the number 1. So the number 1 is the multiplicative identity, the number which, when you multiply by something, gets you that something back. And similarly, inverse. We have to have a multiplicative inverse as well when we're talking about these sorts of properties. So we have a number a, which when we multiply it by some number, we're going to get that identity that we just found back again. Now you might see another problem again, right? A times what gets you 1? Well, for any number you pick, like 2, right? 2 times what gets you 1? Okay, well that's 2 times a half. But now a half isn't on this list. Okay, so here this is saying that for any number a, the multiplicative inverse is going to be 1 over that, just 1. That was my spouse saying goodnight. Anyway, so here we have 1 over a is going to be our multiplicative inverse. So again, here the multiplicative inverse of these integers doesn't exist on this level, so we have to add yet another layer to this. And this is the rational numbers, which in German has something to do with quotient, and so that has a double Q letter as its thing. Again, you don't need to know this, but it's just fun. The rational numbers are going to be given as some sort of a divided by b, where a and b will be part of... This is highly technical notation. So all right, it will look like a divided by b as long as a and b are integers. This is a member of the set. So A and B belong to the integer set that we had up here, and we're going to exclude B equals 0. Because the denominator can't be 0, because that's going to cause problems, and then you don't have a fraction. It doesn't exist, right? Some number divided by 0, that's not a thing. So these are the three basic sets that you need to look at in terms of numbers that you're mostly dealing with right now. Is you have your natural numbers, you have your integers, and you have your rational numbers. There are at least 3 more groups. I'm not going to get into that unless you really want to get into it. And like I said, I've already done this in another video, so if you do want to go back and look at some of the video on demand, you'll see a diagram that looks almost like this, except it's bigger. And you can watch that one as well if you feel like it. Probably not for tomorrow, but after your final's over, feel free to check out. Yeah. After your finals is over, feel free to check out the other stuff. And you can kind of get a grip on like why these things exist and why I'm so excited about it. Hopefully that comes across. So these things actually you do talk about in like Algebra 1 and like what basic properties exist for these kinds of numbers. So the additive and multiplicative, identities and inverses are super important to try to understand like how all of math works. And one of the interesting things is that when I was in, and my spouse as well was also in the math program at the same university, and like all my friends and stuff like that. So when we all took algebra or abstract algebra, we had to go through this, and they said, okay, here's what you know. 0 is not equal to 1. 0 is equal to 0, and addition and multiplication are things that work. Prove the rest of mathematics. Like, prove that the rest of mathematics exists. And I was like, Eventually we did it. It was So you eventually prove that other numbers exist. So the fact that 0 and 1 are distinct numbers from each other proves that also because you have addition, if you add the not 0 to itself, it will create a different number. And then that expands and rolls out further. This is what's called a successive number. So if you just add 1, you get the next successive number. But then you could do the successive of the successive of the successive of 1 or of 0. And it gets you all the numbers from that point on. Then to prove the rest of mathematics, you basically have to prove these identities and inverses actually work. And by the way, here are the rules that you have to work with it. It's not easy. I have actually done a couple of streams on a computer program that like helps you do proof verification. I don't recommend it. I don't recommend watching that one. Okay. Got very quiet very suddenly. I was worried. Anyway. So other properties that exist for this, and then like if you're doing abstract algebra, you have to prove it. But for you can kind of take it for granted that these things exist. You have the commutative property, which allows you to say that if you're adding two numbers, a plus b, that is the exact same thing as adding b plus a. Now, again, you might be like, well, duh. But it's not actually something that you can take for granted for all of mathematics. There are certain portions of mathematics for which this is not true. Now, these values are not necessarily numbers, right? They might have to be some weird thing in the corner of math that nobody ever talks about, but that's the idea. And it also works for multiplication. Again, for numbers. Any numbers that you want to plug in that you have here, your naturals, your integers, your rationals, and in fact, most of the rest of the numbers that you can go beyond that, these properties will work. So, commutative properties of addition and multiplication. The associative property allows you to say, I want to associate certain values with others. So for instance, I want to do a plus b first, and then add c after. With the associative property, if the associative property holds, you are allowed to add a to the sum of b plus c. So you could do whichever one you wanted first. It doesn't particularly matter. And this is actually what I was doing up top. Probably never even noticed it. But I started pulling, what was it? Over here. With these numbers, 2 plus 4 plus 4 plus 9 plus 4 plus 4. I didn't add them in order. I said, okay, this is 8, and 9 makes 17, plus 4 is just convenient. So that's 21, plus 6 was 27. So I added the 2 and the 4 first in my head, and then also started from the right-hand side over here. But again, if you just say, okay, 2 plus 4 is 6, plus 4 is 10, plus 9 is 19, plus 4 is 23, plus 4 is 27, right? If I do it in order, you get the same value. And again, it's something we kind of take for granted. It doesn't always work, and again, it has to be some, deep part of mathematics that we hardly ever bring up. Or if you do that weird thing that they sometimes do in pre-algebra, where they say like, A star B equals 3, or something like this. They put like weird symbols in there that don't actually have anything to do with math. They technically do. It's just that they're not the common notation. So this stands for like doing a particular function. I'm going to do a particular operation, and when I do that operation on A and B, I always get back 3 at the end. So anyway, this is far afield and we don't need it, but the associative property, anyway, will hold for both addition and again for multiplication. So if I want to multiply a times b first and then multiply c, that works just as well as multiplying a to b times c. And often the way that I will indicate to my students which one I'm doing, how I'm associating these things is by vocal pauses. So I will say, for instance, for the first one here, this is a times b times c, whereas this one is a times b times c. For some of them, it drives them nuts, and they're like, that's the same thing. And I said, no, it isn't. Listen very carefully. So the way in which you can vocally say things sometimes indicates what you're doing with this. And it gets a little weird sometimes, but like I said, as long as you're indicating, or as long as you are effectively communicating what you're trying to do to your audience, that's really what matters in a lot of mathematics. There's a couple other properties that still need to be here, so let's see, commutative, associative, reflexive is a pain in the rear. Reflexive property states that A is equal to A. So technically you need to have this, and it needs to be a part of like your system. Otherwise you do not have a, I believe it's a field is what we're looking at. But again, you don't need to know that. If you don't have a field, then there's all sorts of problems. You know, you can make all sorts of assumptions that are wrong. And using all of these together, there's the distributive property, which is that a times b plus c is going to be equal to here a times b plus a times c. And again, works for all numbers, sometimes does not work for other objects, or only works on other objects in certain arrangements. If you've ever seen matrices, a matrix, not the movie, right, the mathematical thing, then it is an array of numbers which look like this, you know, A, B, C, D, like that. And if I tried to like multiply matrices together, it gets really complex. I'm not going to do that. You don't need to know. Unless, of course, you do need to know. But since you said integers, we're just going to be sticking mostly with that. So also using some of these things, we can do some of the like addition, subtraction, multiplication, division that you have done and that we have talked about up top. If you wanted to talk about like some sort of large multiplication, you could do that. So, you know, 6 times 73. I mean, we know it's 438, but how would you show it, right? So let's even go more complex than that. Let's do 60. Let's do 67 times 83. This is a big multiplication, but it's actually very easy to do when you start looking at, in America, it's called the Common Core method. Basically, the idea is to introduce these algebraic properties onto numbers. And you might not even know that you're doing it. I'm not sure how it works up in Canada, but I'm sure you all have pretty much the same thing. But the idea here was that, and my daughter actually just started doing this in 3rd grade math, I think, for much smaller numbers. She was like, yeah, we just use the distributive property. I'm like, I didn't learn that when I was your age. So here, 67 and 83 can be broken up individually into 2 separate numbers. So 67 is 60 plus 7 times 83 is 80 plus 3. These are actually fairly convenient values to use when we're multiplying. Now, what we can do is use the distributive property. And actually, it doesn't matter whether we do left distribution like this, or if we use the commutative property of multiplication, shift the A onto the back side and do right distribution. It doesn't matter. So your choice, whichever way you want to look at it. If we take this and say that this is just this thing on the front, yes, maybe. So I know, you know, the old PEMDAS thing, but at the same time, it doesn't necessarily help you with larger multiplications. Anyway, I prefer to show it kind of using the distributive method, because what happens here is actually once you learn how to do this, doing something like this is trivial. This and that are literally the same thing. Okay, you know, there is a little nuance to this one down here where you have variables. But like as long as you know what you're doing here with just numbers, the variables, they're just the same stuff. Now, you're not going to be doing that until algebra. So whenever you're, no? Okay. Apparently I don't know what I'm doing. Okay, cool. So with this, what we can do is say, okay, I'm going to take this as my A and then multiply it into this B plus C. So this is going to be 60 plus 7, parentheses, multiplied by 80. Oops, I don't need the parentheses here. Multiplied by 80. Plus 60 plus 7, multiplied by 3. And again, you could choose to leave this where it is and do right distribution, or you could bring it to the front and do left distribution. It doesn't much matter. Again, you're using commutative property, you're using distributed property, you're saying that right distribution and left distribution are the same thing. It's all good. It all works. So here, if we do right distribution, we're still using the distributed property. It's just, again, from the reverse side, you're now multiplying this way. You're now multiplying this way. There we go. So here, this is going to be 60 by 80 plus 7 by 80 plus 60 by 3 plus 7 by 3. So now what does that make? Well, you could kind of you could kind of argue what you want to do here. Again, usually what I do is I do the associative property and some commutative property stuff. I say that 60 is the same as 6 times 10 times 80 is 8 by 10. And then shift this around so it's 6 by 8 by 10 by 10. Use the commutative property. Multiply the stuff that's easy to multiply together. Tens, all of them, over there. Sure. All right, 7 by 80 is again going to be 7 by 8 by 10. 60 by 3 is going to be 6 by... Okay, 6 by 10 by 3. Let's literally keep it the same there. And then this is just going to be 7 by 3, which we already know is 21. Here, this is going to be 7 times 8 is 56 times 10. Plus, trade these, 6 by 3 by 10, plus 21. This is going to be 48 is 6 by 8, times 10 by 10 is 100. Plus, 56 by 10 is 560. Plus, 6 by 3 is 18 by 10, plus 21. 48 hundredths. 4,800. Plus 560. Plus, here 18 tens is 180, plus 21. And then here this becomes the same addition thing that you've been doing, you know, probably again, if you're doing American Common Core, this is saying we're going to take this 4,000 and add 800, then add 500, then add 60, then add 100, then add 80, then add 20, and add 1. You don't have to do this, but again, this actually goes all the way down to, like I said, you know, second, third grade math. Like, just thinking about it in this way allows you to break these numbers up, bring them back together, or rearrange them. And again, this is now an algebra problem. This now goes back to, like, how do we do things with just variables instead of actual numbers? Well, if you fall back on using these properties, then doing things with variables is just as easy as doing things with numbers. So, this is going to be 4,000 plus 800, 500 is 1,300, plus 100 is 1,400, plus 60, 80 and 20 is 160. It's 160 plus 1. So then, again, 5,561. A little tedious, but again, at the same time, if you break things down to their smaller parts, you don't have to worry necessarily. 67 by 83, let's hope it comes out right. 5561. All right, cool. So by using all of these algebraic properties on numbers, now you're able to get a little bit of practice on using the algebraic properties, and then when you come across algebraic expressions using variables, these things become second nature. These things. All those properties up there. All those become second nature. So I will applaud the creators of the American Common Core system in terms of that, like being able to understand fundamentally at the base level how mathematics works, and working all of this stuff into elementary school education. Like, that was hard. That was hard work, and they did it. So good on them. I'm one of the parents who does not complain because I understand the math. One of the few parents who does not complain. This is also something that really helps when it comes to, like, at some point I need to take like 73 and multiply it by itself, or square it, in other words. So when I want to square something, this means that I'm going to multiply 73 by itself, so 73 by 73. I could do this just in the same way I did it down here. Yeah. So squaring something is most conveniently used for area. However, it doesn't have to be, right? It could just be some number that you're multiplying by itself for whatever reason. Again, for applications, that's the easiest way to think of it. There's also, for instance, if you want to talk about like an object that's getting thrown through the air. So you take an object and you throw it. It will follow this parabolic path that it goes as it goes through the air. So it's going to go up, and then it's going to reach a maximum, and then it's going to sink down. And the path on which it goes is very predictable. Now, I will grant you one thing inside of Earth's gravitational field that you do have to worry about is typically atmosphere. So there is a wind pressure to slow down the object, and it will have a terminal velocity. So it has a maximum speed at which it can go down. For the most part, we can ignore it. And so in mathematics, we tend to ignore it because it's fine. But like the height of an object is going to be given by, and don't panic, again, you probably don't need this or anything, but negative in terms of meters. This is negative 4.9 t squared when we're talking about t is a time. And then plus v0t plus h sub 0. v0 is just the initial velocity. h0 is the initial height. And t, both in terms of this t here and this t here, are just time in seconds. So the reason that this one works and why it's squared has to do with the fact that this term is dealing with acceleration. And the units, when you're talking about acceleration, in this particular case, is going to be meters per second per second. So meters per second squared. You've probably heard of these terms before. You know, anyway. This is the speed at which the speed increases. So you drop an object, and it's going to gain actually double this amount. So it will actually gain 9.8 meters per second of speed every second that it falls. So this is why, like, falling from higher and higher heights is extremely dangerous, because inside of a gravitational field, the gravity pulls at the same amount, but as it keeps pulling the same amount, you end up going faster, because it's still pulling on you, and it's still making you come toward the Earth faster. Right? The Earth wants everything around it to sink down to its center of mass, which is at the core of the planet. It wants everything to sink down to that point. It can't do that because the density of the rock around it is so great that it's holding everything else above the rock. So now we, life forms that live on the Earth, are basically just floating on a giant floating piece of rock inside of a sea of gas that can't sink below the rock. Food for thought. All right, this is height in meters. So, like, if you end up with a particular scenario, so you know that you throw a rock at like 5 meters per second upward, or 10 meters per second upward, and you could plug that into the initial velocity portion. And then you know that you are standing at a height of about 5 or 6 feet, or, well, okay, 2 meters when you release this object. Then you can plug those values in for the constants, the initial velocity and the initial height, and to within a very small degree of error, you could find the exact location, the exact height of that rock as it's flying through the air at any given moment in time. So if you took a video of you throwing the rock from like a side view, and you throw this thing, you could see it follow this very closely to parabolic path. And you could find the exact equation that governs its height at any given time. You could do the same for it governs its height at any given distance. So squaring numbers is used for all sorts of stuff. A lot of times, if you're talking about distances, the acceleration term has a squared term attached to it because, again, the distance that something travels inside of an accelerative field, inside of some sort of, I hate using the term, but a field containing forces. So yes, a force field. Right? A gravitational field is a force field. It's just not the sci-fi force field where it blocks all movement and stuff like that. So a field of forces that are pulling toward the center of a planet, or what have you. You could have like a magnetic field. All right, it doesn't have to be gravity, but gravity's a nice, easy one to do. So when you're squaring stuff, there is a predictable pattern that always exists, no matter what numbers you plug in here. And it's pretty awesome. So if you break up 73 into 70 plus 3, and you've got 70 plus 3 on the other one as well, note here that we have a 70 times a 70, and a 3 by a 3 all the way at the end. And in the middle, we have a 3 by a 70, and a 70 by a 3. But by the commutative law, those are the same thing. 70 by 3 and 3 by 70 are literally the same thing. So you could actually rewrite this as 70 squared plus twice 3 times 70 plus 3 squared. That may not necessarily get you somewhere faster, and that's fine. But this has a very important implication in terms of algebra when we get to stuff later on. And this is actually what my entire channel is named after. So N Simplex Pachinko is named after taking a plus b and raising it to an nth power. And in fact, way far afield, but you could have more terms than this on the inside. Raising it to a specific power, and then figuring out the play that occurs between all of the individual numbers. So if we raise something to the 0th power, for example, 0th power means we don't have any of these things. However, we do have a 1. This is a plus b to the 0th power is just going to be equal to 1. Any number raised to the 0 power, as long as it is not 0 itself, is going to be 1. All this really is saying is that a and b have to be distinct numbers. They can't be the same as, or they can't be opposite each other. So 2 and -2 are not going to work. But anything else. If we wanted n equals 1, then this is going to be a plus b raised to the 1st power. Well, raised to the 1st power, it's just the thing that we had. So this is a plus b. N equals 2, we end up getting the same pattern that we had up here. We have an a plus a b times a plus b. Well, this is the same thing. The 70 can be replaced by a, and so now 70 squared is the same as, oops, a plus b parentheses squared is going to be a squared. This is 2 times plus 2 times. A 3 times a 70 is the b times the a, or, swap them around, a times b. Plus 3 squared, that's the b term, so that's b squared. So the a squared plus 2ab plus b squared is going to be generally any number that you want to square it, you can end up with this exact same formula. So if I want to take, you know, I don't know, make up any number you want. So 41 squared, or 99 squared, or, and actually that one's, there's a bit faster way to do that one, but we're going to let that go for now. So, you know, 99 squared, or 37 squared, or any number that you want that has 2 digits in it, you can end up doing this process, following this rule here, and getting that number much faster. So when I'm doing this in my head, and yes, I do 2-digit squares in my head very easily, I'm doing this. I'm saying, let's take the first number and square it. So 70 squared is going to be 7 times 7 times 10 times 10, if you remember, right? 7 times 10 times 7 times 10. So rearrange. 7, 7, 10, 10. Makes 7, 7 is 49. 10, 10 makes 100, so 4,900. Plus 3 times 7. You can go about this a couple of different ways. Again, this one's not too bad. So 3 times 7 is 21. add a 0 on the end is 210, times 2 is 420, plus 3 squared is 9. 49 plus 400, 4900 plus 400 is going to be 53. So this is going to be 5,329. So 73 squared is going to be equal to 5329. And again, I will do this process in my head every single time. I want to square a number. I'm going to multiply it as if they were this binomial squared. So I'm going to take the first number and square it. That's going to be a hundreds term. The last number, square it, and that's going to be my ones term all the way at the end. And then the middle terms are the hard part. So you have to do twice those two numbers multiplied together. And again, do it in my head, fairly easy. Yeah, so one of the reasons that, or one of the reasons that my channel is called N-Simplex Pachinko is that this actually creates a picture as well. So you could create the awesomeness that is this thing by saying if we had a field of just zeros everywhere and they're inside of little hexagons, at some point somebody puts a 1. Now the rest of the hexagons everywhere on the entire field are zeros. This is the only one that exists for the moment. As we come down, what we're going to do is say we want to take each of the hexagons that are there. You kind of have to imagine them here, just sorry. And what we're going to do is to get the next number down, what we're going to do is add the 2 hexagons that are touching it up above. So usually the hexagons will be shaped kind of like this. And again, anything that's blank is a 0. So everywhere up from all of these are all going to be zeros forever and ever and ever, in every direction except downward. When we want to find what number is in each of the hexagons below the ones that exist, we're going to add the ones that are above it. So to get this one here, we add a 0 and a 1, and we get 1. To get this one, we add a 0 and a 1, and we get 1. To get this one out here, it's a 0 and a 0, so that's going to be a 0, so it's blank. This is zeros out here as well. Going down from here, we're going to have, again, 0 and a 1 is 1, 0 and a 1 is a 1, but now the middle one gets a 1 and a 1, and now we get a 2. Notice now, these are the same coefficients that we had here. A 1, a 2, and a 1. I can then build this out and make as many rows as I want to get. This has been called the Pascal triangle, mostly because Blaise Pascal, a French mathematician, did this work with relation to probability and statistics, and found that if you wanted to, for instance, flip a fair coin twice, then your 50-50 probabilities would be given by each of the A's and B's that are here. So they're all going to be 0.5 going all the way across. And if you want to know how likely is it that I'm going to get one head and one tail on 2 flips, then you look at this middle term here, which has A1, B1. And I'd say that it's a 2 times 50% times 50%. 0.5 times 0.5 is going to be 0.25, and then multiplied by 2 is going to get us a 0.5. So we have a 50% chance of getting one head and one tail on 2 flips. And if you look at the experimental data or anything like that, you find that that's true. One of the other things that you can do is, instead of leaving it like, or yeah, we could talk about n being the number of flips. So like if we wanted 10 flips or something, we could continue this all the way down as far as we wanted to go and find out how likely it is that any particular combination of heads and tails is likely. All right. In addition, we could change the probabilities. So if the coin is unfair, if it is slightly weighted or very heavily weighted toward heads rather than tails, you could reflect that inside of these probabilities. So how likely would it be if it were 90% heads and 10% tails? How likely would it be to have one of each on 2 flips? Well, that's still a 2 times a 0.9 times a 0.1. 0.9 times 0.1 is 0.09, and then twice that is going to be a 0.18. So there's an 18% chance that you are going to get one head and one tail on 2 flips of an extremely unfair coin. That particular extremely unfair coin. And then I figured out that you don't have to limit this to 2 dimensions. So if I want to do a plus b plus c, so let's do 142 squared. If I wanted to do this, I could do this just as well. It's going to come out with something a lot uglier and a lot nastier, and yeah, I'm probably not even going to show it, but this is actually what's on my streams. This thing at the bottom left corner. I can't show you because it's a static picture. I'm circling it with my mouse. You can't see that. So we get this 3-dimensional object, which is at the bottom left corner, where we have a certain number of times that it's going to fall into each of the... this is a ball that's going into the these hexagonal prisms. And the probability that it's going to fall into any one of these things on the bottom row weighs very heavily with the thing that I just was talking about here. So if we have a plus b plus c raised to the 2nd power, you know, this is the same as falling into that pattern that we had, which was 1, 2, 1, 2, 1, 2. So how likely is it that it would fall into any one of these bins, essentially? Ooh. Oh, that's ugly. Alright, whatever. How likely would it be that it would fall into any one of these bins? Well, each of these individually has these probabilities. It would end up being like A, B, C, like this. So we have 1a squared plus 2ab plus b squared plus 2bc plus c squared plus 2ac. It's like this would be the whole thing that we'd have to look at and then try to figure out the polynomials and the possibilities. And this would actually be done kind of the same way. If you wanted to, you could write this out just the same way. This is 100 squared plus 100, whoops, twice 100 by 40 plus 40 squared. Nope. Yeah. Plus twice 40 by 2 plus 2 squared plus twice 100 by 2. It's like, what are all the different combinations? These are all the different combinations you can get. When you want to multiply it out as an actual number, these are all the combinations as actual numbers. And so we'd have to add up all these things individually. Obviously, the larger this number gets, the more unwieldy this becomes. At that point, like if I'm doing higher dimensional stuff, or if I'm going to go down several layers here and get like a big triangle with a whole bunch of bins going like this, I'm going to start using a computer. Let the computer figure it out, because this is going to be impossible to try to figure out by hand. Not impossible, but extremely time consuming to figure out by hand. So this would be a three-digit number like 142 raised to the, I don't know, like 7th power or something like that. You could figure out what that is, but again, it's just really big and really unwieldy. I'm trying to figure out some cool stuff with programming and trying to determine if there is a pattern within all of this stuff that I can break, and then maybe I can publish a paper on it. But anyway, it'd be kind of interesting. So I've monopolized this time a bit. But if you have any questions, let me know.
Only you had a motive for murder.
18,000, 19,000, 20,000, 64. Now I could have missed something here, but let's see. 142 squared, 20,164. Okay, I missed it. Yeah. What was the? Oh, right, the one that's the one that's right there. 164. All right, so not too bad, but you just have to watch your bookkeeping, like I clearly failed to do. All right. Well, Cloud Floof, if you're still here, thank you very much. And if you're not here, if you came back watching the VOD, whatever, thank you very much for coming and having some fun interacting. And again, if you have any questions, let me know. If anybody else out there has any questions, let me know. Either come back on some future Wednesday night, or again, I might do some random math streams. They usually have to be after 9 p.m. just because that's when kids are out doing whatever. But at some point over the summer, I may start doing like a one-off or two-off here and there. Just have a few more, like 1 hour long streams, something like that. Yeah, no problem. Like I said, thanks for coming. It's great always being able to interact with people. Like I said, if you weren't here, I'd be teaching to an empty room, and that'd be fine by me. But it's much more interesting to have interaction. So hope to see you again. And I'm gonna set up a raid. So if you want, you can hop along and oops. If you want to, you can hop along and even if it's just for like a couple minutes, support whoever it is that I'm gonna pick tonight. So who do we have? It's also a good question. If not, you know, I'll probably just see you around, but all right, who do we have?